We started talking about electrons and a little bit about waves and electromagnetic radiation, if I'm not mistaken. That's what we talked about previous to that. I think that's where we laid up last time. So last time we were talking really in relationship here to sort of what we're talking about in this chapter is we're talking about really electrons, and as electrons really start to transition from different energy levels, they either have to gain enough energy to do that and take them from one energy level to the next, or they have to lose enough energy, obviously, to drop down from a higher energy level to the next. The result of that is, as we talked about with sort of conservation of energy, is we're not going to lose any energy, but energy will be sort of given off, especially in the transition when electrons start to drop back down from a higher energy level to a lower energy level, just like obviously energy would have to be sort of gained as it goes from a lower energy level to a higher energy level. As they sort of transition, they will give off this energy, usually in the form of a wave, a photon of light. And as we talked about, you know, if it does fall in a specific part of this electromagnetic spectrum here, for example, the visible part of the spectrum, we will see colors like the red, orange, yellow, blue, and all those kind of guys. And that's sort of what we're going to do today in lab with the flame test. You're basically going to excite all those electrons. They're going to try to transition down in terms of energy. It will give off light, and you'll see different colors in the flame as those electrons are transitioning and that energy is being given off. Not always will you see sort of colors. It can come off anywhere else in this sort of spectrum. And then you might not actually see sort of a color as a result of that. There is a relationship, as we talked about, with waves and energy and frequency. So if we have a wave that has a fairly long wavelength, which is lambda, that means that it is a lower energy. So remember, guys with longer wavelengths have much lower energy as a sort of longer frequency. And that's different than if we have, you know, a wave such as this, which has a much smaller wavelength and a smaller wavelength, a higher frequency, and a higher energy associated with it. So this guy usually has a higher energy. So if we look on this side of the spectrum, like we talked about, I think at the end last time, this is a much larger wavelength than over here on the other side. And that means on the right-hand side, where we have things like radio waves, it's going to be obviously lower in energy than, as you can imagine, something like gamma rays or X-rays, which has a very short wavelength, high frequency, and a high energy. We can even, as we talked about in terms of colors, also sort of break them up. Red here, having the longer wavelength, is actually lower in energy in terms of a color versus sort of the violet side here, which has a much shorter length, higher frequency, and higher energy associated with it. Any questions on that stuff there we're talking about? We also talked about the idea of sort of quantized energy, which is basically the idea, and we'll see that probably a couple more times here, that, you know, basically electrons, for example, will gain enough energy to fully transition from one energy level to the next. They won't find themselves, you know, sort of in between energy levels. And that's the idea of sort of quantized energy. I think I talked about the stair sort of example. You know, you have enough energy to give you on one step or the next step. You don't usually stop in between. And that's sort of how electrons transition. They transition in that effect of gaining or losing enough energy to completely do the transition from one energy level basically to another. So that is what we were talking about there, that sort of quantized energy. And there is actually a formula that you can use to calculate the energy associated with a wave, for example. And that is E equals H times the frequency here. And these guys here, H is a constant. H is what is referred to as Planck's constant, which is 6.63 times 10 to the minus 34. Frequency is this guy here, and that is in reciprocal seconds typically. And that means when the units cancel, we are left with joules for the energy here when we use this guy. This equation also ties into one that we saw earlier as well, which I believe was C is equal to the wavelength times the frequency. C is the speed of light. which is also a constant, and that's that 3 times 10 to the 8 meters per second. The wavelength is obviously lambda, and obviously our frequency. And you actually could substitute this in because you could solve for the frequency. The frequency would equal c divided by the wavelength, which means if you take E is equal to h times the frequency, you could calculate the energy by simply just knowing the wavelength by using this version of the equation where h is a constant and c is a constant, which means really all you would need to know is actually the wavelength of a wave, and you'd be able to calculate the energy associated with it. If you do use that equation, the wavelength does need to be in meters for everything to properly cancel out in terms of units. But that's a very useful sort of one. Or if you have the frequency, you could just go into obviously this equation here to calculate the energy. But yeah, this does definitely need to be in meters, again, for everything to sort of cancel out correctly. Any questions on that? We're not going to do too much calculations with that equation. You'll see it again when you take 1A, but you'll do calculations there. But those are two equations that will pop up commonly with sort of waves and wave sort of function. Oops. So this is, again, ultimately what we're sort of focusing in on in this sort of chapter here is the transition. And when we do get that excited atom, and you could excite an atom many different ways, again, like we're going to do today, we're just stick it in the fire. Obviously, that's going to add enough energy to get all those electrons moving. You could, run electrical current through it as well. We'll do that as well. And when we do get these electrons really excited to a higher energy level, as we talked about, that's really not an ideal situation in chemistry. Things really do want to be in the lowest state of energy as possible. So what they want to really do is sort of relax themselves back down into a lower state of energy. And that is, we can see here in this picture, as it does so, it does have to give off that excess energy in the form of a photon. So we would see red light obviously being emitted in this sort of situation here. The release of that energy is going to allow that excited lithium atom to basically drop back down to a lower state of energy, a little bit more stable of a situation than where it was when it was excited. Again, you probably have done sort of like a flame test like we talked about, I think the other day. If you just boiled water at some point and it overboiled and you had salt or something in it, and it's usually salt, you'll usually see the flame sort of change color, kind of goes orangey yellow really quick. And again, that's really exciting, the sodium ions that are in the water and stuff like that. Especially if you're cooking pasta, you might throw extra salt in there, so you might actually see a little bit more of that occurring. So this brings us to an idea of Bohr's theory of hydrogen atom. And when we do get those atoms basically, or electrons transitioning from different energy levels, they will sometimes give off what is sometimes referred to as an emission spectrum. An emission spectrum is usually what occurs as those guys are transitioning from higher energy level to lower energy level. Basically, the atom is emitting off that energy, right, to the surroundings. And we can see this, we can basically see two types of emission spectrum. One is what is referred to as a continuous spectrum, where pretty much we see everything come out at once. So all wavelengths sort of come out as is given off. And as we'll talk about here in a second, something like the sun does that. We see color, heat, everything is sort of coming off all at once. And more importantly, though, atoms and elements really give off what is sometimes referred to as a line spectrum. And we'll see some examples of that in just a second. But a line spectrum is pretty much what is given off by atoms because of this quantized energy, where we have these specific transitions that occur between these electrons in a different energy level. And it is what it sounds like. They give off specific lines at different wavelengths of light that correspond to different colors. And you could look at a spectrum using something like a spectroscope, which has a prism, separates out the light, and you'll see these distinct lines occurring with different colors in the visible part of the spectrum at different wavelengths. And that is typically how sort of elements, when they're excited, either through adding heat, electrical charge, whatever it may be, sort of give off their emission spectrum as those electrons are transitioning. Now, not all sort of emissions, as we talked about, will always be sort of a visual representation in that visible part of the spectrum. You can have obviously energy being given off with a wavelength that corresponds, as it says here, to the infrared part of the spectrum, maybe the UV part of the spectrum. And, we sometimes do see that occur. When we see something like a metal sort of heated, we can see the glow of it. We can also feel the warmth coming off of it. So there's a lot of different wavelengths coming off. And that's sort of a continuous sort of spectrum. So like the sun, and when you heat solids like that, we get basically everything coming off at once. So in sort of a representation, like we were talking about elements, and they give off this sort of quantized energy where we have sort of these steps, if you will. You can think of like a continuous spectrum as sort of like a badly drawn here ramp. We'll see a better picture in a second, but like a ramp where pretty much if you're walking up a ramp, right, you technically could stop anywhere along the way, right? There's really no problem with you just kind of stopping anywhere along the way if you're just kind of walking up a ramp. You obviously typically cannot stop anywhere along the way when you're going up like stairs, right? You got to be on one step or the next step or something like that. And that's sort of the visual sort of difference between a continuous spectrum. Everything just kind of comes out, energy, and everybody can stop anywhere along the way, versus this quantized energy where we see with elements when they are excited. So the emission spectrum of atoms in the gas phase really don't show that. They do show this line spectrum. One nice thing about a line spectrum for our elements is every single element has its own unique line spectrum. So if you look at different elements and you're not really sure what you're looking at, maybe you've done this experiment before in the past, perhaps, they put on like a lamp, right? It has a little bulb in it and it kind of glows. You look at it, you see lines. You can look at these different sort of elements, gas discharge tubes, and you'll be able to really determine, what element you're looking at based on the actual lines that you see, the colors that you see, and the actual wavelengths that those guys are coming off. And what each of those lines really do represent when you look at a line spectrum, for example, we'll just call it a red because I got a red here. So we got a red particular line. It's really representative of an electron transitioning now from one energy level to the next, giving that off, and that will correspond to, for example, a red line that you would see within the sort of red part of the visible spectrum coming off. Depending on how many electrons are moving around, you may see multiple lines. You may see stronger intensity lines, because when we think about this, sometimes we think about as the electrons are transitioning, we sort of think about it like one atom at a time. But obviously, if you have a sample of an element, is multiple, lots and lots of atoms, which means each of those atoms are having these transitions occurring, which is why we get these really distinct sort of bright lights and lines that come out when we do it. Here's an example of hydrogen. So when you look, for example, if you put hydrogen in a gas discharge tube, run electrical current through it, excite all the electrons in hydrogen, these are the typical lines that you see, which corresponds basically to the transitions that occur in hydrogen. And just by looking at sort of the wavelengths here, we can make really a deduction of energy and how far these electrons are going. As we talked about before, which one is lower in energy? Which color is red? Red is lower in energy, versus here, which is purple violet, which is higher in energy. Which means we're talking about in terms of transition is perhaps the red electron is just transitioning, correspond perhaps to this red line, as opposed to a lot more energy as it drops in lower energy, which would result in more energy being given off and more of that purple line sort of happening there. So, based on the lines that you see where they are at energy, you can make a rough estimate of, how much energy is being given off. By the way, we could even, if we wanted to, take that, which is the wavelength, and put it into our equation we just talked about, we would need to convert it to meters, and we could actually calculate the energy associated with that wave that comes off. And when we would do that, we would see what we just talked about, that the guy on the left there would probably have a much higher energy than the guy on the right. Again, that's a result of it transitioning more energy levels than the red guy on the right there. But distinctly here, hydrogen will typically always show these sort of 4 lines. And again, different elements will have different lines that will appear at different ones. And each of these lines, again, is basically representative of a transition of an electron from a higher energy level to a lower energy level. Now, sort of a idea of the atom was one that was sort of developed by Bohr's model of the atom. It works really well for hydrogen. It works really well to explain sort of the lines that we just saw there on that chart that we do see in hydrogen. Unfortunately, it sort of falls apart as you move away from one electron, like pretty much everybody but hydrogen. So as you move away from sort of one electron, it doesn't really hold sort of true really well, but it does explain what we do see in hydrogen. Bohr's model is obviously very complicated. We're not going to go into great detail about it, but the idea of Bohr's model is one where it's sort of a planetary model where he envisions we have the nucleus and we have these electrons basically traveling around in orbits, which, as talked about previously, not really correct at the end here, but sort of this idea that, you know, we have these nice pretty circles around the nucleus. We have electrons that are sort of restricted within these orbits as they're traveling around. And his vision was, again, what describes sort of those lines that we see in hydrogen is, again, an electron traveling from sort of one orbit to the next and making that transition and giving off, obviously, that energy associated with it. So because electrons could only be found in certain orbits, they were restricted to really traveling those until they sort of transitioned down. He did also sort of label the different orbits and energy by energy levels, which is N. N is sort of what is referred to as the principal quantum number. And that's a really fancy words for basically the energy levels. So when we have something like N equals 1, as we will see, that is basically the lowest in energy you could have. It is sort of what is referred to as the ground state, low in energy. Anything above N equals 1 are what are basically referred to as excited states. So his idea, again, is we have these electrons, and as it transitions from one energy level to the next, the atom is going to give off that energy in the form of a photon of light corresponding to the energy levels that we do see. As we'll talk about in just a second, you know, there's really, you know, no good way to know how a particle like an electron is traveling at any given time or its path. And so that's why sort of the Bohr model doesn't hold up so well as we continue on in this sort of version of the atom here. So again, here's a maybe prettier picture, that sort of orbital with our nucleus to the middle, our electrons sort of traveling. So the emission of radiation, as we see different colors, again, is that electron dropping down, giving off a photon of light with a specific color. And when we talk about energy levels, as I mentioned, N is what is referred to as the principal quantum number. It really is sort of a fancy way to describe what energy level a particular electron's on. When you take 1A, you'll learn about all the other quantum numbers. There's 4 different quantum numbers, basically. There's N, L, M sub L, and M sub S. And they basically revolve around how we were going to talk about here at the end of this chapter, electron configuration. But they talk about basically where electrons could be, what energy levels there are, what possible places you could find electrons. It's really what all the quantum numbers really sort of represent. in terms of chemistry here. But n equals 1 is the ground state, so you can think of it as really, sometimes drawn like this as well, just, it's the lowest energy level you could have. Anything above that, like n equals 2, n equals 3, n equals 4, those are what are referred to as excited states. Higher in energy, further away from the nucleus as you go up. N could go from basically 1 through 7, basically, is the possible values that you could have for that. And by the way, if you look on the periodic table, there are 7 periods, and that basically corresponds to each of the n numbers that you see if you go that way. So here, as we were talking about a second ago, much prettier picture, but we see this transition of an electron starting here and coming down just sort of one energy level from a higher state, giving off a color like red, as opposed to the electron that started up here, obviously passing through multiple states there, which means it has to give off a lot more energy. And we see it does correspond to that more higher energy color, bluish in that particular case. So you can make, like I said, a pretty good assumption based on the colors that you see as to the energy and how much transitioning is occurring between the different electrons, how far they're basically traveling based on the colors that you see. These are the transitions that really do correspond to the 4 colors that we do see in hydrogen. And again, you can see, this energy level here versus this guy that came all the way down here, much more energy and stuff. So each of these transitions will result in different colors that we see based on, where they start with in terms of their excited state to where they sort of end with when they release that energy as it comes down. And again, this is sort of an idea of quantized energy versus continuous energy. Again, something like the sun and sort of heated metals will give off basically a continuous one. And you can see pretty much you're going to get everybody all the way along the way. You can pretty much stop anywhere along the way. And on the right here, we could have only these discrete sort of states where we could find a particle like an electron being. And again, that's really the idea of quantized energy is, we'll either find the electron here, we'll find maybe the electron here, but again, we'll never find like the electron just kind of hanging out right there in the middle. It's got to either be on one of these sort of energy levels. It will never just kind of hang out in the middle. You can't hang out anywhere here because technically it's just a continuous stream of energy and everything being given off. So like I said, it's kind of like the ramp explanation there. You can stop anywhere along there as you're walking up. And here's the ramp and then prettier stairs. So as I said, Bohr's model was a pretty good idea. It described really well for hydrogen, but it really didn't hold up as you sort of moved away from hydrogen with a lot more electrons sort of involved. So a few other guys sort of came along that sort of moved us away from sort of Bohr's idea of an atom and these orbits and electrons traveling these pretty circles to a more mechanical sort of explanation of it. So one really important part was a guy named de Broglie. Actually didn't do an experiment. He just basically thought about it. And it's basically that I came back to the idea of sort of the dual nature of light, that if we have particles that can have wave-like functions, waves could have particle-like functions. So a particle such as an electron can behave very much like a wave. And that's sort of the idea here. He thought of waves as like standing waves. So the idea there is, when you pluck like a guitar string, right, it's pretty much locked into place, but you still get obviously the wave that occurs. And there's points along the way when you pluck that string, right, where there's basically no amplitude. And that's what's referred to as a node. And it's sort of the same idea that what he was thinking about was that the nucleus has a positive charge, right? And electrons have a negative charge. So, they are sort of tied to the nucleus in that sense, that there's going to be some attraction to it. And, it's going to be giving off some energy as they start to transition from these different energy levels. So the idea here was that particles like electrons can have what are referred to as wave-like functions, which we're not going to get into any of those wave functions in here, but um, it led to the conclusion that, you know, we have these particles like electrons having these wave properties. And what this essentially is doing is sort of moving us away from the idea of Bohr and this sort of orbital model of these electrons for sure traveling these nice pretty circles, and you know, you could put your finger there and wait for it to come back around, and you know, you'll eventually hit the electron as it does come around the orbit. Another big sort of moving away from the idea of sort of the orbits and really for sure knowing how electrons are moving was done by a guy named Heisenberg, and that's the Heisenberg uncertainty principle. And basically that's the one that says it's pretty much impossible to know simultaneously how a particle, for example, like an electron, is moving and its location at any given time. And really the idea is if you know more about one of those things, so if you know more about sort of the location of a particle, you know less about how it's moving and vice versa. So there's this uncertainty in sort of how a particle like an electron that can have wave-like properties is really traveling. And again, that is again moving us away from Bohr's idea that I know for sure it's in this orbit and it's going around in a circle, to really sort of the idea, as we've talked about a number of times, that you know, electrons really do have sort of a random sort of pattern as they're moving around the atom. And the best that you could do, as we'll talk about here, is say, you know, I think there's a very high probability that in this part of the atom, we could find an electron. We don't really know sort of where it's at, how it got there, how it's moving, but we think there's a pretty good chance that, you know, at some point, there should be an electron, you know, in this part of the atom, versus for sure, like in the Bohr model, that I know for sure it's in this orbit and it's going around in pretty circles and stuff like that. So the last part of it came with a guy named Schrodinger, and he had a bunch of equations. If you ever take physical chemistry, you'll remember this guy for sure, with a lot of math that's involved. But basically his idea, again, sort of tying on to this idea that things like electrons that are particles could have wave-like function, came up with really this idea of more of a probability and probability map. And basically we think about electrons not really being in orbits and going around in circles, but we think about them being in what I refer to as orbitals or atomic orbitals. And these are really sort of theoretical probability maps of, you know, there's a pretty good chance that we could find an electron in the atom in this particular sort of area. Again, not knowing when it's going to be there, how it's moving, but, you know, there's a pretty good chance. So if we just think about logically, you know, if we have our nucleus, you know, there's a pretty good chance that, you know, near the nucleus, we would have a good chance of finding an electron there, as they are negatively charged, the nucleus positively charged. Probably makes sense that they're going to hang out there. Again, as we sort of travel out from the nucleus, the probability really starts to decrease. I think we might have saw a picture of it earlier. We'll see a picture in just a second, but they sometimes will express this in sort of degrees of color. So kind of a darker color, like a pink, for example, is a very high probability of finding an electron in that area. And then as it sort of fans out for where the nucleus would be, we find a sort of lower probability of that. When we talk about atomic orbitals are these sort of probability maps where we find electrons. And this is an electron density. And again, hopefully up there, you can kind of see it, that kind of darker area, you know, we would envision that the nucleus there is in the center. And you can see, obviously, the color gets a much lighter, which means we're getting less of a probability as we sort of move out from the nucleus of sort of finding an electron. We think about these guys as atomic orbitals where we find electrons. And as we'll talk about here, there's basically several different types. There's s orbitals, p orbitals, d orbitals, and f orbitals. And we'll take a look at what these guys kind of look like here in just a second. But these are sort of the probability maps of within an atom where we would expect to sort of find electrons. And these orbitals are also found at different energy levels within the atom. So we have these different energy levels within the atom. On these different energy levels, there's these different sort of atomic orbitals where we can house electrons. And we're going to talk about how to properly put the electrons into these guys as we go through it. So let's talk a little bit about the atomic orbitals. The first type of atomic orbital are s orbitals. S orbitals are really just spheres. And by the way, one really important idea about orbitals is that any individual orbital can hold a maximum of 2 electrons. So any individual orbital that you come across, the maximum number of electrons that it could actually hold is actually 2 electrons. And that's an important thing to keep in mind. So an s orbital is really a sphere. And on the very first energy level, n equals 1, which is the ground state energy level closest to the nucleus, that is where we find an s orbital. And that is what is referred to as a 1s orbital on the first energy level. S means it's the type of orbital that's there. Orbitals on every single energy level. So every single energy level has s orbitals. So if you went to the second energy level, which would be higher, obviously, than nucleus, except that it's on the second energy level. So it is referred to as the 2s orbital. 2 meaning it's on the second energy level, and obviously s meaning the type of orbital. If they are a sphere or a circle, if you will, they do get sort of larger as you go up in energy levels to sort of accommodate all the orbitals and electrons that sort of come with it. So what we're talking about here, if we use an arrow to represent an electron, we could only put 2 electrons into the 1s orbital on the first energy level. If we had more electrons, we would then need to jump to the next energy level and put those electrons into that one as well. Electrons, as we'll talk about, basically go into the atom lowest energy first, fill up all those orbitals, go to the next lowest, fill up those, go to the next. So electrons always go into the atom lowest energy first and kind of fill its way up. Here is again, sort of our electron probability map or density map, and this is sort of what a s orbital looks like. And the idea here is that this dark area in the middle would correspond to sort of the nucleus. And again, we can see that darker area where we have a greater probability of finding those electrons. As we go up, a 3s orbital, a little bit larger, obviously, than 2s and a 1s, but they all have the same shape. 3s means we're on the third energy level, like n3. This guy, again, on the n equals 2 level. This guy would be on the first energy. With an energy here, this direction, again, they just look the same, a little bit larger to accommodate all the electrons that are sort of there before them. The next type of orbitals are what are referred to as p orbitals, and p orbitals do not begin until you get to the second energy level. N equals 2 is where we first start to see p orbitals, and then we see p orbitals pretty much after that. And there's 3 different types of p orbitals, actually. We'll come back here. There's the px, py, and pz orbital. So on the first energy level, the only thing we have is a 1s orbital. When we go to the second energy level, we have a 2s orbital, and that is where we first start to see p orbitals occur. And that is the 2 p orbitals. Again, that is px, py, and pz. Px, y, and z is like math, right? The Cartesian plane there on different axes, x, y, and z axis. There are 3 of them together. They look like what we see here on this picture here. They kind of look like figure 8s or teardrops. This sort of area is kind of thought of like where the nucleus is. And we can see here, this kind of darker area here is again where our highest probability of finding electrons within a p orbital. And again, one obviously on the x, y, and z. This is the 3 different p orbitals. when we take these three p orbitals together, they are sometimes referred to as a subshell or sublevel. So this is what is sometimes referred to as the 2p subshell or sublevel. Within that subshell, it basically contains three individual p orbitals, which means if I max out the number of electrons there, how many total electrons have I filled up all three of those? 6. Each one could hold 2. Yeah, so technically, if we filled up the 2p subshell with electrons, we would max out at 6, 2 in each. Because s orbitals only have basically one orbital, there's no real subshell or sublevel associated with it. It's just an s orbital, which obviously has 2 electrons that you can put in there. Any questions on that? Again, you do find them on every other level besides that, but they do start at the second energy level, and then you have it on third energy level, which would be a 3p orbitals. Fourth energy level will be 4p orbitals, and so forth as you continue up the energy chain there. The next type of orbitals are d orbitals, and d orbitals actually don't appear until the third energy level. So on the third energy level is really where we first start to see d orbitals appear. There's actually 5 different d orbitals. They look like this. They kind of look like 2p orbitals that have been stuck together, and one in a donut here at the end. But we still have a 3s, we have a 3p, and here is where our 3d orbitals really start to first appear. Same thing here, all 5 of these individual d energy level are referred to as a shell or sublevel, depending on your book. And if I filled up the entire d subshell, how many electrons could I put in it? That would be 10. Yeah, so I can put 10 electrons, 2 into each of them if I fill them up completely. The next sort of orbitals which are important are actually f orbitals, and they appear on the 4th energy level. Let me actually go back here. On the 4th energy level, we actually get f orbitals. They start at the n equals 4 level, and at the n equals 4 level, you have everybody else still there, a 4s, a 4p, a 4d, and then pretend that's 7 of them, a 4f basically appears, you know, coming up there. So it's not until the 4th energy level, or n equals 4, that we do see the f orbitals basically appear. And there are 7 of them, by the way. There are 7 different orbitals or f orbitals, which means for my f subshell, if I filled it up completely, we have how many electrons? There's 7 orbitals, and I fill it up completely. 7 times 2 is 14. Yeah, so 14 electrons. So really important for where we're going here is really talking about electron configuration. How the right electron configuration is to know the different orbitals and basically know how many maximum electrons you could put in there. And you should be able to write pretty much any electron configuration that you need. Do these guys really exist within the atom? The actual answer is probably not. These are, again, are just sort of probability ideas, mathematical representations of where we find these. You cut open an atom, where you see these like shapes? Probably not, but they are, you know, really, you know, sort of these probability and ideas. Again, moving us into that idea of not really knowing exactly how a particle like an electron is moving. So a couple of things just to touch upon here as we continue on, but first off, a couple of terminology things which are important. All right, so as we talked about a second ago, there's about the subshell and everything like that. If we were asked a question about like the n=2 level, that is what is sometimes referred to as a level or a shell. For example, we would be talking about n=2. So if I ask a question like how many maximum electrons, if you filled up the n=2 level, the answer would be, it would be yes. So we could go 2 here, right? We could go and 2 in each of these. And that's a grand total of 8. As we talked about before, if we want to know the maximum number of electrons in a 3p subshell, that would be how many? Again, the subshell or sublevel refers to a group of orbitals on the same energy level like that, right? Which means we could put in there 2, 4, and 6 electrons, right? How many electrons in a 3D orbital? How many electrons do we think? That's close. So 10 would be not the orbital. 10 would be if we took all these together, which is referred to as a subshell, right? But an individual orbital could be that d orbital, that one, or that one. Any individual orbital can only hold 2 electrons. Yeah, so an individual can hold 2 electrons. If the question was, you know, how many electrons in the 3D subshell, the answer would be 10. Yeah, in that case. Yeah. Question.
So when is there, once you increase each orbital, or can you proceed to the next orbital without having every orbital or subshell full?
So yeah, I do understand what you're saying. So your question is, do you have to fill the orbitals below to go to the next one? And the answer is yes. So the electrons would come in here first. Once that's filled, it would then go here. Once that's filled, it would go here, and then it would flop up here and continue that pattern. So you do have to fill all the orbitals that are in the lowest energy first. And at some point, you'll run out of orbitals on the energy level, still have electrons. So you then got to put them somewhere else, which would be the next highest energy level. Yeah. And you would continue that pattern. We're going to talk about the actual order in just a second, but you would continue that pattern and fill the lowest to the highest, and you don't skip any along the way.
So it's predetermined?
It is predetermined in terms of, because there's technically these orbitals in an atom, every atom, along with these different energy levels, based on the number of electrons there are in an atom as to, you know, how far up you go, basically. Yeah. Question or yeah? Yeah. 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 We're actually going to talk about that in just a second, but there is an actual order when there's different ones. The quick answer is they actually go into one at a time and come back and fill they go back and fill. Yeah. So we're going to talk about all that coming up here. So why don't we get into that? So again, here's just that representation of our pictures of what they look like as we continue up. Now, with something like hydrogen, when there's really only one electron present, hydrogen, right, has just one electron. When we look at the orbitals on each of the energy levels, and obviously this would be n=1, n=2, n=3, and so forth. What we see is like all the orbitals on the third energy level, they're like perfectly equal in terms of energy. When we start getting a lot of electrons involved, electrons are negatively charged, right? Which means as we start putting them into the atom and they're in the atom, we got negative things near negative things, which really don't want to be near each other. It actually makes an effect on the energy that we see for these orbitals. And we actually get a change in where these orbitals end up. And as you can see, as we move past one electron, we no longer have everybody on the third energy level really the same exact energy. And that is going to affect sort of your question of, you know, where's the electrons going to go first? And they're going to follow that. The big difference is not 1s, the next lowest is a 2s, and then to the 3p, then to the, I'm sorry, 3s, 3p. The big difference is here. It's actually the 4s orbitals end up being d. So if somebody you can up here, electrons will actually end up over here in the 4s, and then they'll go back to the 3d. And that pattern follows as well. You see here 5s is actually lower in energy than 4d. So there is an important sort of order at which the electrons go into the atom based on the energy of these different orbitals. And it happens that they really do sort of move around as we get a lot of electrons and negative guys near each other and trying to move away and finding a happy spot. So this is sort of the chart that you can make and follow to write pretty much any electron configuration you want. We always start up here. And basically, we just follow the arrow. So if we get to the end of the arrow, we pop back this way, get to the end, pop back this way, and we basically zigzag back and forth. And as you can see, if you follow the arrows, we get to the 3p, followed by the 4s, and then back to the 3d. So this will give you pretty much the correct electron configuration. Nice thing about this is you essentially make it yourself on a piece of paper. We talked about on the first energy level, what orbitals do we have? 1s, right? The s's start on the first energy level. It's not until we get to the second energy level that we have the p's, right? Not until we get to the third energy level, we have the d's. Not until we get to the fourth energy level that we have the f's. And pretty much all you have to do is just put the numbers down below it and just keep going, you know, all the way down. And you can basically recreate this for yourself very quickly by kind of filling it in. Obviously, this would be 3p, this would be 4p, 4d, and you basically could recreate this really easy for yourself on a piece of paper. You just draw your own arrows and stuff like that. So if you know this, and you know what we talked about before, that the maximum number of electrons in an s orbital is 2, and a p subshell is 6, and a D subshell is 10, and an F subshell is 14, you pretty much should be able to write any electron configuration that you need to do by following this pattern. Any questions on that there? All right, so let's take a look at writing some of these and how we go about doing it. Again, following this sort of pattern here. All right. So electron configuration basically displays how the electrons are distributed within the atom. We basically could figure out how many electrons there are in a neutral atom by looking at the atomic number, right? The atomic number, which is our number of protons, tells us how many positive guys we have, which means if they are neutral, we need to have the exact same amount of electrons that are present. And let's take a look and do some here, I think. Actually, I'll go back. Oops. All right, let's see here. Let's go here. Let's just start with hydrogen, for example. Hydrogen is number 1 there on the periodic table. That means it has 1 electron. We would start at our zigzag guide there, and it would be 1s1 would be the electron configuration for it if you start at the very top of that zigzag thing. What does each of these things represent? That is the energy level, or the N number. The S is the orbital or subshell it's in. And the 1 is how many electrons there are. There are in that orbital or subshell. So again, the first one tells us it's on the first energy level. The S tells us the orbital which the electron's in, and the number on top tells us basically how many electrons are in that orbital, or if it's a subshell. This is what is referred to as electron configuration. It is written like this: 1s1, where the 1 is a regular number, the S is a lowercase s, and the 1 is a superscript on top. No commas, no dashes, no crazy things. We could also do what is sometimes referred to as the orbital diagram. The orbital diagram is either a box or lines that you use to represent the different orbitals, and we use arrows to represent the electrons that are there. So if we did hydrogen, we would have one box which represents the 1s orbital, and whenever the electron goes into an orbital, the first one is always designated by the arrow pointing upward, and that has to do with what is referred to as a spin, which we're not going to get into, but it's basically a quantum number. But usually the notation is always the first electron goes up as well. Any questions on that there? Now, if we look at helium, which is number 2 there. Helium, which is 2, which would be 1s2, 1s2. There is a rule, though, about how the electrons go into it. And one rule is what is referred to as the Pauli exclusion rule. And the Pauli exclusion rule basically says that no 2 electrons within the same orbital can have the same 4 quantum numbers. And although we don't really talk about all 4 quantum numbers here, the 4 quantum numbers are N, L, M sub L, and M sub S. M sub S is what is referred to as the spin quantum number. And it basically has 2 values. It has a value of when the electron goes upward, of +1/2, and it has a value of -1/2 when the electron is pointing in the downward fashion there. Now, if we look at something like helium, which has 2 electrons, we would do the electron configuration as 1s2. Now, when we go to do our sort of orbital diagram, we would have for helium 1 box for the 1s orbital. And we have a couple of choices. We know the first one goes up. We could put the next one up as well, or we could do up and down. When we do put the second electron in, it never points in the same direction. We won't go through it, but if you did the 4 quantum numbers for both of those electrons in the box here on the left, they would all end up with the same 4 quantum numbers, which violates Pauli's exclusion rule. To get around Pauli's exclusion rule is we need to put the second electron pointing in the opposite direction, which means it has an opposite spin as the first electron that's in there. And this is really the way the second electron goes in. First electron always up, second electron always down. When you have 2 electrons in the same orbital, opposite spins, this is what is referred to as being paired spin. The spin is paired. They kind of cancel each other out, if you will. Yeah, one goes up, one -1/2 plus 1/2. They kind of cancel each other out, and that's what's referred to as paired spin. So when putting electrons within the orbital, first one always goes up, second one always goes down within the same orbital, and that means that you will not violate Pauli's exclusion rule, and those guys will have 4 different quantum numbers when we look at it. So that does occur obviously here with helium. And again, following our path there, 1s2 is the electron configuration. And again, our box here, first electron going up and second electron there would go down to fill it. Any questions on that there? At this point, if we think about our sort of little graph, we have now done that. Can I put any more electrons into that orbital? I cannot, right? Which means I do need to kind of head up to the next lowest, which would be on our 2s. If we're following our zigzag, we would come back now to the 2s orbitals. And that's where we would put the next electrons, which happens with our friend lithium there. Back in. So lithium would be 1s2. And again, now that we filled that, the next on our chart would be 2s1. And if we did the orbital diagram for lithium, we would actually need 2 boxes, one for a 1s orbital, one for a 2s orbital. And again, the electrons would go in, as we talked about, up, then down. So that now is paired off and the spins are paired in that orbital. The next electron should go in the next one, pointing which way? Should be pointing up, right? Again, the first one will go in there. By the way, if we count up the top numbers, that tells us our total number of electrons we put in there. 2 and 1 is obviously 3. By the way, in this case, we have how many electrons on the first energy level? 2, and on the second energy level, we have 1. Yeah, so again, you could get a lot of information from the actual electron configuration, you know, where those electrons are at and what energy level they're on. Any questions on that there? Continuing on, I go the right way. Beryllium, which is 4, we can go 1s2, and now we could go 2s2 as we had room to put one more electron into that guy. We would still have our 2 boxes here for our orbital diagrams. One going up, one going down, one going up, and now we can pair off the electrons here in this last orbital, which would give us 2s2. We now have 2 electrons on the first energy level, and we have 2 electrons on the second energy level, or the n equals 2 level in this particular case. Any questions on that there? Continuing on, number 5 on the periodic table is boron, which means it has 5 electrons. By the way, can I put any more electrons in that 2s orbital here? I cannot, so I need to follow my zigzag guy and come to the next one, which should be our 2p orbitals. And here we would have 1s2, 2s2, 2p1. In this case, we would need several boxes. We would need a box for the 1s, a box for the 2s, and because the p orbitals are a set of 3, we would need 3 individual boxes for those guys. That represents our 2p orbitals. The filling of it will go like we did, 1 up, 1 down, 1 up, 1 down. Now we have some options as to where we can put the next electron, and the next electron will go in this very first box, which is really the px box. By the way, the one next is the py, and the guy at the end there's the pz. So the very first electron here will go up, and it will go in the box on the far left there, which represents the px orbital. How many more electrons can I put in that p subshell before it's full? Yeah, we could fill it up with 5 more electrons before we really run out of room, before we need to go anywhere else. Now on the next guy, which is carbon there, we are going to have 1 more electron, and now we have a choice or where we should put it. Will the electron pair up here? Would we put it in somewhere else? There is another sort of rule that helps us decide sort of where to put the next electron, and that rule is what is known as Hunds Rule. And basically Hunds Rule says that the most stable way for an atom is to maximize what is referred to as parallel spins. So if you remember, we just talked about that when the electrons go in opposite of each other, that is paired spins. Parallel spins is everybody heading in the same direction. And what that means is when we come across something like our p subshell, which has our px, our py, and our pz orbital, what ends up happening is the very first electron comes here, and to maximize the parallel spins, the next electron would go into the next orbital, and then the next electron would go into the next one. Again, maximizing all those spins going in the same direction. At that point, you have no choice. You got to start pairing them up. And we do come back afterwards on the 4th one here and start pairing them up one at a time, coming in this direction. So when we come to orbitals or subshells that have multiple orbitals, they go in one at a time, and then you come back and pair everybody up. And that's the proper way to distribute the electrons within a subshell that has multiple orbitals. Question on that? Yeah. Yep. Either way.
So I'm curious, or I'm stuck in this space, like as you build in the energy levels of the orbital, and you say the weakest ones would put up first. So for example, maybe 4s would fill first before you get to like 3D, even though that's on the energy level below. So if you're gonna lose electrons, will it pull from the weakest first? And if it does,
Yeah, we'll actually talk about that, but typically the electrons will come from the highest energy level first. So if we think about what we talked about in terms of energy, highest energy is kind of unstable, right? It's not really what things want to be in. So with electrons, kind of works the same way. When electrons are lost or pulled, if you will, they do come from those highest energy levels because, frankly, if they're in the highest energy level, they're the furthest away from the nucleus. They're not held as tightly. They're easier to pop off. That's up, yeah. Yep. Other questions? Okay. All right, so let's take a look at carbon then. So carbon would be 1s2, 2s2, 2p2. Again, our orbital diagram filled out correctly here. We'll have our boxes. We're going to go up, we're going to go down, we're going to go up, we're going to go down, we're going to go up, and we're going to go one more here again into the second box there to maximize that parallel spin. Continuing on, might as well finish out the first row there of 10. So coming up would be nitrogen, which has 7. And obviously we can see we have room for that guy going to end up in this box right here. So we would do nitrogen, which has 7 electrons. Electron configuration would be 1s2, 2s2, 2p3. And again, our orbital diagram. Up, down, up, down, up, and up. At this point, we could put how many more electrons into our 2p subshell? 3. At this point, we've really maximized our parallel spins as best we can. So we have no choice for the next electron. Obviously, it needs to come back and start pairing up those guys to completely fill up those orbitals and get everybody sort of in the right location there. So continuing on here for number 8, which would be oxygen. Oxygen would be 1s2, 2s2, 2p4, where our 4th electron there is where we're going to start pairing up as it comes in. So up, down, 1, 2, 3, and now our 4th one is paired. You can see that we pretty much have room for 2 more electrons there on the back 2 boxes. And that obviously happens with fluorine, which is number 9. The next paired up would go to the center guy. The last one, obviously, to the guy on the far right there. So let's just finish those guys out there. So number 9, which is fluorine, 1s2, 2s2, 2p5. And there, and we could clearly see that pretty much everybody's filled except for this last orbital here, and that is again going to obviously be filled when we hit over there to neon in this particular case. By the way, how many electrons do I have on the second energy level? On this one, I have these guys, right, which is 7 electrons, right, counting the top numbers. And still 2 there on the first energy level, right? So we have 7 electrons on the higher energy level and 2 on the lower. Those ones on the higher energy level are what we refer to as valence electrons, which are the highest energy ones there. And let's fill up the last 10 here with neon, 1s2, 2s2, 2p6. Coming up, coming down, and obviously we'd go one at a time and now come back and fill these in. And now we have completely filled this up. We cannot put any more electrons, obviously, into the 2p subshell. We would then have to travel to where next would be the 3s orbital would be where we would come next. Any questions on that there? All right, why don't you try something? Why don't you try, let's do chlorine. Why don't you try chlorine, which is 17. Try the electron configuration and see what you end up with. Okay, let's take a look. So 17, starting at the top, you should have 1s2. That fills that up. Swinging back around should then take you to 2s2. That should fill that up. Next one should be our 2p6. Again, if you count up the top numbers, you got 2, 4, and 10. So we got 7 more to go. After that, we should then go to the 3s2, which takes us to 12. And finally, after the 3s, we should fill up our 3p to only 5 in this case, right? Which would give us 17. And that should be the electron configuration. And I'll just steal down here, this guys. We would have one for 3s, which obviously would look like this. And for our 3p, we would again need 3 boxes where we would go up, 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 down, and down. And that's what the orbital diagram would look like if this was chlorine, right? Any questions on that there? All right, we will lay it up there for today.